Suppose you have a bunch of points thrown down at random on the number line. Here I have 5 points, U1, U2, U3, U4, and U5, which are IID uniform on 0, 1, so I've thrown 5 darts at the unit interval. When you look at those points, you can't actually see which was the first point that I threw down. Any one of those red points could have appeared first. In the end, what you see are the 5 points in sorted order. And the elements of that sorted list are called the order statistics. So U parenthesis K is called the kth order statistic, as you read, and it is the kth smallest of the lot. Any one of the points that you threw down is equally likely to be this particular one, but we don't know which one. And what we're going to do is we are going to see if we can find the joint density of any two of them. The method that we use is going to be quite generally applicable. You can use it to find other joint densities as well. So let's give ourselves a problem to find the joint density of the second and the fourth smallest. So U parentheses 2 and U parentheses 4. Now, these are two random variables. Both have values between 0 and 1, but the second, U4, must be greater than U2. So if I look at the unit square, and I decide to draw U parentheses 2 over here and U parentheses 4 over here, then all the action is in the upper triangle. There's no density, that is, the density is 0 everywhere else. So our job is to find the density for points where x is less than y. And what we're going to try and do is we're going to look for the probability that x is just around some little x, and it's not x, it's called u2. u2 is just around some little x, and u4 is just around some little y. And for this, we should have a picture. And I'll remind you, before we do that there are 5 points in all, and we're just looking at the second and the fourth. Okay, so I'm going to try and redraw the unit interval. I'm going to put down an arbitrary dx and an arbitrary dy, and before doing anything else, please remember that dx is not where the point is. The point is x, and this point here is y. Dx and dy are little intervals around, infinitesimal intervals, right? So you should imagine them to have essentially no width. And they're also representing the width of those intervals. And what I want is for the second one to fall in that little dx and that fourth one to fall in that little interval dy. And the others have to sort themselves out in the other three intervals. And now what makes life easier for me is that I don't care where in those intervals they land. I just care how many are in which range. So let me see if I can actually use colors to sort out what the categories are. I've taken a continuous problem and I've made it a discrete one. Either the point falls in that region or in this one or in this one or in this one or there. So I have divided the unit interval into 5 categories. And what we're going to do is count how many points must fall in each category for this event to occur. And it is clear that number 2 from the bottom better fall here, and number 4 from the bottom better fall here. Now, please remember that when you have two random variables with a joint density, they can't be equal, and we're going to let dx get very small. You should be imagining it as an infinitesimal, so there can only be 1 point here, not more than 1. After you get small enough, you're not going to have collisions. So there's 1 in that green tiny bit, and there's 1 in the pink tiny bit, and now we have to work out how many there are in each of the other bits. Well, if the green bit is where the second one is, then there better only be 1 before that. So there should be 1 in the yellow interval. And then so we've got 1, and now the green is the second one. The pink one has to be the fourth one. So therefore you should only have 1 in here. And so now you've used up 4, and there's 1 left, and that fifth one better go in the final interval there. So the event that the second smallest is in dx and the fourth smallest is in dy is the event that there is 1 each of the 5 in each of those 5 categories. Now you are throwing darts down independently at random. Any dart could fall in those 5 categories, and they're independent of each other. So what you have are 5 multinomial trials, each of which can land in any of these 5 ways. So you really have a multinomial probability here. And now the multinomial starts with a combinatorial term, which is the number of trials factorial divided by the counts in each category factorial. So I have 1 factorial, 5 lots of these. Yes, I know it doesn't make any difference numerically, but it helps remind us what's going on. So this is just an extension of the binomial, which is trials factorial divided by successes factorial, failures factorial. This is the multinomial coefficient, which you've known for a while, and this just splits that denominator into all of the different categories. And now what follows is for each category, it's the probability of that category to the power the number in that category. So now if I look at this yellow category, this is the interval from 0 to x. The random variables that are falling are uniform on 0, 1. So the chance that a uniform is in any particular interval is just proportional to the length of the interval, and the length of this interval is x. So we're going to have probability of the yellow category to the power number in the yellow category. And then 1 has to fall in dx. The chance that a particular one falls in dx is density dx. And then another one has to fall in that orange interval. That orange interval has width y minus x. and the count has to be 1. And then I have a 1 dy to the power 1. I'm just running out of space. And then I have my final blue interval has length 1 minus y, and that also is to the power 1. So there's that long string of probabilities. These are multinomial probabilities, basically p1 to the n1, p2 to the n2, p3 to the n3, etc. 5 of those terms. And so now we can calculate this. 5 factorial is 120. The denominator is all ones. So then I'm going to ignore the dx's and dy's for now. I have an x, and I have a y minus x, and I have a 1 minus y, and then I have dx and dy. And I'm done. I'm done because I wanted the joint density of these two random variables, and I found this joint probability here, the chance that one of them is in dx and the other one is dy. And I know that once I found that chance, the density is everything in that chance except the dx dy. The density is the chance relative to the dx dy, so it's just there. And I'm done. I have my joint density is f of x comma y is 120 x, y minus x, 1 minus y for 0 less than x less than y less than 1. And some of you will recognize this as the joint density with which you've been working in your exercises in the previous parts of these lectures. This is how I came up with it. I wrote down a bunch of uniforms and I decided to find the joint density of the second and the fourth. You could find the joint density of the first and the fifth, or of the third and the fourth, or any pair that you want, following exactly this process. What you're doing essentially is you're turning a continuous problem into a discrete one. Just realizing that all that matters are some finite number of segments of the unit interval, and then you just have a multinomial problem. So this method that has been used here, you can adapt to find the density of any single one. You can also find the joint density of 3 of them if you want a density whose possible values are in the 3-dimensional space. This is a very typical way of finding joint densities of random variables which have some physical construction like ours did, where you are throwing down points and then you're looking at them in sorted order. If you can use a method like this to find the chance that your points are in some tiny region, from that you can extract the joint density.